Now let's do another example. And this is, we have an inclined plane and this is an ice slope or a snow slope, and there's no friction, and we have a sled over here sitting on it, and well, it's going to slide down, and we don't want that. So there's a tree over here, and we tie a cable to that tree, and we make sure that the cable is parallel to the ground, just to keep the problem simple. Now the cable is going to pull the tree this way, which we're not concerned with because we don't want to find the force on the tree. In this way, the cable is going to pull upwards. That's the tension in the cable. The weight of the sled is vertically down, which we write as mg. The normal force is, that's the ground. Normal force is perpendicular to the ground. And now we want to find, again, what is the tension. So there are, well, many ways of solving this problem. And first I'll show a method that is not generally used, and then we'll go on to the one that we will use. So if I consider x to be horizontal and y to be vertically up, not perpendicular to the surface but vertically up, then I would need to break up all the forces into x and y components. This already is in the y direction. The t will have a tx and a ty, and the normal would have an ny and an nx. Now, if this angle is theta, then this angle is theta, and this angle is theta. And sum of forces in the, let's say, well, we can do any first. Y is 0 because there's no acceleration. Then the first force is ny and ty and mg equals 0. Now ny, that angle is theta, is going to be n cosine theta. So now the y component is theta because that's the angle theta, not this one. And ty is going to be, that's the angle theta, so ty is the opposite, so it's going to be t sine theta and mg. So that's one equation. And now we go to sum of force in the x direction is 0. So we have tx and nx. And that's it, only two forces. And tx is going to be t cos theta. And nx is going to be, well, here, n sine theta. So the x component here is sine theta, the x component here is cos theta. So now that's the second equation. So we have two equations and n and t, two unknowns. So two equations with two unknowns, we can simply solve them. However, it's going to be a somewhat longer solution. So we use another way to do it, which is the one that's used in this book and also in most of the textbooks. And so before I do that, I'll just draw this again. So here's our object. Mg is straight down. The tension is this way. Normal is this way. Now what we do is, instead of taking xy like this, we take x this way along the ground and y perpendicular to the ground. So we tilt. Here the coordinate axes were horizontal and vertical. Here we tilt the coordinate axis. and that makes the problem much simpler. So now all the forces need to be parallel and perpendicular to these, so we need all the x and y components. This is in the x direction, that's in the y direction, this is not, so we have to break this up. We need one component that's in the y direction, so it's going to be like this, and one component that's in this direction, so you can draw it here or we can draw it here. So drawing it here sort of completes this right angle triangle. So this side, this angle is theta, and by trigonometry this angle is theta. This side becomes mg cos theta, and this side becomes mg sine theta. Opposite to that is the sine theta, even though it's in the x direction. And now we write the sum of forces in the, let's say, y direction is 0 because there is no x. Well, this is static equilibrium, so it's going to be n minus mg cos theta, and that's it, only two forces, and therefore n equals mg cos theta. So we have the normal force straight here, and we didn't have to do the simultaneous equations. And then we do the sum of forces in the x direction equals 0, so we have the t to the right and mg sine theta to the left equals 0, which gives us t equals mg sine theta. So if we know the mass and the angle, well, we have the tension. So it's a rather quick solution. Instead of having to solve simultaneous equations, we have the answer right away. Now let's consider a similar situation in the non-equilibrium case. We don't have the string here, so this sled is going to slide downwards, and we want to find the acceleration. So let's consider the slope this way, and we have a car, and the person parked the car but did not put it in park and did not apply the brake, and if we start with the initial velocity of 0, and we know that the car is going to start sliding downwards. We want to find its acceleration, and this angle is taken as theta. So again, the weight acts vertically down, and always try to make a nice figure. If this is the horizontal, the weight will be perpendicular to, or vertically down. The normal will be perpendicular to this surface. That's the normal, that's the mg. And we'll take the x direction along the ground and the y direction perpendicular to the ground. So we break this up into one that's in the y direction, and that's going to be mg cos theta. This is theta, so this is theta, and here is mg sine theta. Now we write sum of forces in the x direction. Well, let's first have the y direction. Fy equals 0. Well, no, how do we know it's 0? It's ma in the y direction. So the force in the y direction are the normal force and mg cos theta, and these are the only two forces, and they equals may. Now we don't expect the car to start flying in this direction, and we don't expect it to penetrate the ground, because this is the ground, it's going to go into the ground, so we don't expect that. So this is 0, and so the normal force is mg cos theta, as before in the previous problem. And now we write the sum of forces in the x direction equals max. Okay, these were the non-equilibrium problem, that's why we're not writing it to 0. So in the x direction, that's the only force, mg sine theta, and there's only one force, there must be an acceleration. The masses will cancel, and we have ax is g sine theta. Okay, so the acceleration is going to be g sine theta. When theta is 0, sine theta is 0, there's no acceleration. So on a horizontal surface, if it's moving, it will keep moving with a constant speed. And as theta gets bigger, sine theta gets bigger, and ax gets bigger. When it becomes vertical, this is 90, sine 90 is 1, and a becomes equal to g. Now, lastly, we have one more example, and that is for multiple objects tied together. So this one's so let's suppose we have a inclined surface and we have a pulley over here, and there's a string attached to the pulley. There's a mass over here, and this mass can slide downwards. The string goes over the pulley and comes here, and there's a mass hanging here. Now this is mass m1, this is mass m2. Well, if the pulley is attached here, if m1 is large enough, it's going to go down, and m2 is going to go up. If m2 is large enough, it's going to go down, and m1 is going to go up. Let's assume that m2 is going to go down. So it will have an acceleration downwards, and therefore it will have an acceleration upwards, because if it goes down, it has to go up. The acceleration has to be exactly equal, because they're tied together. So you can't make one go faster than the other. At any point, the velocity of 2 will be the same as the velocity of 1. Now, let's draw the free body diagram. So we have m1g pulling downwards, and there's a tension, let's call it T1, pulling upwards. Okay, and then over here we have m2g pulling downwards, normal force perpendicular to the ground, and the tension is pulling upwards. Let's call this T2. Okay. So this weight pulling down creates T2, and this weight pulling down creates T1. And well, there's no friction, so these are all the forces. Now we'll take the x and y coordinates like this, and here this will be the y and this will be the x. So this is x and y here, and this is x and y here. Now you can do that. In the book they've taken this as the y. Well, some other people do that also. They take this as the y, and then the y goes along this way. But this is easy enough. So now for m1, there is no x, only the y forces. So we write the sum of forces in the y direction equals may. We have a T1 going upwards. Well, before we do that, let me make a statement that T1 equals T2. And this will be true if the pulley is massless and frictionless. If the pulley has no mass and has no friction, then T1 equals T2. If the pulley has a mass, or if there is friction over here, then T1 is not equal to T2. So we will assume the pulley is massless and frictionless. That's a sort of idealization that doesn't exist. But if the pulley's mass is small and the friction is small, we can assume they're almost equal. So this is T minus m1g equals m1a. So we could write ay, but a is in the y, and there's the same a here and here, so no need to write a1 and a2. And then we must write m1 because we're considering this mass. This mass is not included in this equation. the effect of this mass is in here, in T. It's in here. So we have one equation. Now we consider M2. For that, let's write the equation in the y direction. We'll need to break this up first. So this will be M2g cos theta and M2g sin theta. So in the y direction, we have the normal and M2g cos theta, and there is no acceleration in the y direction, equals 0, and therefore the normal force is equal to M2g cos theta. So we have one equation here, we have one equation here, and now we write the sum of forces in the x direction. So we have this one, M2g sin theta, that's in the x direction, and minus T2, but T2 is the same as T1, so minus T. Only two forces, equals M2a. Now this acceleration was positive, so we left it as a, and this is also positive because that's our positive direction, so we leave it as plus. If this were going down and this were going up, we would have written a negative here and also a negative here. Now that's the third equation, and this equation will not help us much in this problem. So we use T from here in here. So this becomes M2g sin theta, and T is going to be M1a plus M1g. Okay, we bring the M1g here and bring it down here, equals M2a. Now in this equation, if we know the masses M1 and M2 and the angle, then a is the only unknown, which is the same a, so we can rearrange that and solve for a. Okay, and that it can be solved. Okay.